Let's start the last lecture. So this is a very short lecture. I already wrote down the lecture notes on the blackboard. At the last lecture hour, we discussed the example of this in the textbooks. And this example is the exercise to learn this kind of quantum mechanical measurements, in particular multiple measurements, probability to actually get some eigenvalues after, say, a second measurement. But we need to study what happened after the first measurement. So this exercise tells us that the first measurement of the Sx for a spin 1/2 system leads to this eigenvalue plus h bar over 2, but their second measurement is done just right after the first measurement. And the second measurement is on this new operator, Sx cosine phi plus Sy psi phi. And the question is to access what is the probability that the second measurement gives you still plus 1/2 h bar. Okay, so this is something that you need to calculate, you need to be able to calculate, okay, by the end of the semester. This is simple, but you need to think about this calculation in a quantum mechanical way. To solve this problem, there are two steps. Okay, the first step is to find out this initial state after the first measurement. Okay, so the first sentence is that the first measurement is done for Sx operator for the spin 1/2 system, and the final answer after the first measurement is plus 1/2 h bar. Any measurement can only give you all the possible eigenvalues. So this tells us that the eigenvalue for the Sx after the first measurement is plus 1/2 h bar. So then what is the corresponding eigenstate, eigenvector, after the first measurement? So this is something that you are able to do. So this is easy because the first part of the question is to ask you the eigenvector of the state after the first measurement. Okay, so then you can simply just solve the eigenvalue problem for the Sx, and this is Sx in terms of the Pauli matrix sigma x, and this two-spinner U and V is the eigenvector for Sx. But we are interested in this plus 1/2 h bar as the eigenvalue because we know already that after the first measurement is done, this is the result. So we need to find out what's the eigenvector corresponding to this plus 1/2 h bar for Sx. Okay, so and this is very easy to do. This is the eigenvector, square root 2, the 1 over square root 2 times 1, 1, this two-spinner. So you plug in this eigenvector, and you get this eigenvalue equation satisfied, which is the eigenvector for lambda plus of Sx. Okay, so then we answer the first part of the question. So the second part of the question is, given this initial state, which is the state after the first measurement. So our initial state is the state after the first measurement, which is the eigenstate of Sx with the eigenvalue plus 1/2 h bar. So the second measurement is done for this operator, and we know very well that the final result can be one of these possible eigenvalues of this operator, right? Okay. Based on this kind of a Fourier decomposition theorem and this statement that any arbitrary quantum state could be expanded in terms of complete set of eigenstates. Any arbitrary state is the initial state. Our initial state is any arbitrary quantum state, which happens to be the eigenstate of the Sx with the eigenvalue plus 1/2 h bar. But it doesn't need to be. It can be any state. But any state could be expanded in terms of the eigenstates of whatever operator. But whatever operator, in this case, is this Sx cosine phi plus Sy psi phi. That operator is the whatever operator. But we already solved this eigenstates of this messy operator. The final result here, alpha plus is the corresponding eigenvector or eigenstate for the eigenvalue plus h bar over 2. Alpha minus is the eigenstate for minus h bar over 2 as the eigenvalue. And we already did that exercise last time. So we take advantage of our previous knowledge. You plug in this kind of expansion. Any arbitrary quantum state could be expanded in terms of eigenstate of whatever operator. And this whatever operator is this operator, and this corresponding eigenstates are alpha plus and alpha minus. So this initial state could be expanded in terms of linear combinations of this alpha plus and alpha minus state with a corresponding coefficient MB. This is a very simple algebra. You can solve this coefficient MB. By the way, this coefficient MB are called probability amplitude. So it's from the first chapter of quantum mechanics. And the probability that this measurement gives you this plus h bar over 2 is nothing but a squared, or the square of the magnitude of a, which is cosine squared phi over 2. So the calculations are really straightforward, but the important point is the concept, the quantum mechanical concept. What is the measurement? Okay, what are the possible answers after the quantum mechanical measurements? What are the initial states? What are the possible results after the second measurement? The results after any kind of subsequent measurement can only be one of the possible eigenvalues of whatever operator that you want to measure. Any arbitrary state could be initial state, and initial state could be expanded in terms of the linear combinations of the complete set of eigenstates of whatever operator. You could go on and ask the similar question if I continue performing the third and the fourth and infinite number of measurements of whatever operator, and what is the probability that you get the answer to be plus or minus h bar over 2. You should be able to find out this answer after infinite number of quantum mechanical measurements of this sort. Good. So now we are done with this spin 1/2 for a single particle. I sketch this addition of two spin 1/2 spins. The last part of the lecture, we don't have time to finish this derivations, but let me just highlight. Suppose we have two electrons, such as helium or other spinful particles. We could add up all this spin making moment together to form the total spin of the system. We can define the total spin operator S as the sum of these two individual spin 1/2 operator S1 and S2. Remember, either S1 and S2 or S2 satisfy this commutation relation for the spin angular momentum operator. S1 commutes with S2. But we could define the total spin operator S or Sx and Sy, and they also satisfy these commutation relations for the total spin. But more conveniently, we would define this eigenbasis for this for the total spin variables. Each of these two individual spin 1/2 object as a combined two spin 1/2 system, we can describe the system by using this complete set of a commuting set. Okay, so this could be this commuting set consisting of this S1 square, S2 square, S1z, and S2z. There are four possible states for this two spin 1/2 system, namely plus plus, plus minus, and minus plus, and minus minus. So this labels the eigenvalues of the S1z or S2z. So this plus plus refers to the states that this S1z is plus 1/2 h bar over 2, h bar over 2, and this S2z is again plus h bar over 2. Similarly, plus minus refers to the first spin with the z components plus h bar over 2 the second spin carries the eigenvalue of minus h power over 2, and so on and so forth, so minus, plus, and minus, minus. But these four possible eigenstates of this 2 spin 1/2 system could be described equivalent way, meaning we could use a different commuting set to describe the 2 spin 1/2 system. And inside this commuting set, we have the total spin s squared, total spin as z, and s1 squared, s2 squared. A shorthand notation is this total spin s, this as z. Okay, so there are two possible eigenvalues for this total spin. Consists of 2 spin 1/2. One is spin 1, another is total spin 0, because if you consider 2 spin 1/2 object, they could be either parallel or anti-parallel together. These two are parallel, you get spin 1, but if they are anti-parallel, they get cancelled. We could describe this four states in terms of the total spin variables: total spin s, total spin sz. So this plus plus state is nothing but this state called 1, 1, where this s is 1 and m is 1. This minus minus state is nothing but this 1 minus 1 state, where this total spin is 1, but this m is actually minus 1. So remember, when the total spin is 1, you get three possible states, which we call the triplet state. For spin 0, total spin 0 state, it is so-called singlet state. So this triplet state, there is a middle state called the 1, 0 state, which means that the total spin is 1, but m is 0, which is linear combinations of plus minus and minus plus with the plus sign and divided by square root 2. And the singlet state is actually a state orthogonal to all the three states, which is 1 over square root 2 times plus minus 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 plus state. So we don't have time to derive such a correspondence, but you could read our textbooks, and using this total spin quantum number, we could very conveniently construct additions, the total spin of the system, because many properties are determined by in terms of the total spin variables. Such a triplet and singlet states could be found in many well-known examples in quantum mechanical systems, such as the helium atom. We know that helium atom consists of, say, 2 electrons and, say, 2 protons, 2 neutrons. There are many other examples of this triplet and singlet states that you can find in quantum mechanics, but you could first read our corresponding chapters in this chapter 10. Okay, to summarize, so I think I have given you the clear key and fundamental concepts of quantum mechanics, starting this kind of Heisenberg uncertainty relations and particle wave duality, this kind of a probability interpretation of a measurement and quantum states. And then we introduce this Schrödinger equations for one-dimensional potential problem, and then harmonic oscillator, and then we study this operator method, especially this Dirac notation, and then angular momentum operator, and so on, hydrogen atom. So I hope you get complete pictures of is important and fundamental in quantum mechanics, and you are welcome to study further by either sitting or taking this advanced quantum mechanics course given in our department. So I thank you for your participation. Wish you all the best with the flying color. Okay, see you around.